welcome to part 2 of the quarter 4 review where we'll cover organic and nuclear. So for organic, the most important thing that you need to realize is that organic is all about the element carbon. In fact, when you look at the reference tables at table P, I think this one's table P and table Q, you'll notice that they're all about carbons. For example, the prefixes that help you to identify the carbon chains, you should realize it says right on the table that it's associated with the number of carbon atoms. And table Q, it's a homologous series of hydrocarbons. What do we mean by hydrocarbons? Hydrocarbons are the parent chain for many organic compounds. They are hydro and carbon. They contain hydrogen and carbon only. Okay? And so when you're talking about a homologous series, you might be asked about homologous series. Go to table Q because it tells you the 3 homologous series you need to be familiar with: alkanes, alkenes, alkynes. Notice that the endings of alkanes, alkenes, alkynes are relevant because the name, if it's an alkane, it has an ANE ending, an alkene, an ENE ending, and an alkyne, a YNE ending. What's the difference between them? Alkanes are all single bonds. Alkenes have 1 double bond. And alkynes have 1 triple bond. Okay? Alkanes, alkenes, alkynes. Now, if they're all single bonds, remember we sounded like a snake, single, saturated. So the saturated compounds are alkanes, whereas unsaturated are alkenes and alkynes. Remember to remind yourself, saturated is single bonds. Now, the other thing that you should realize is that what makes an alkane, alkene, alkyne a homologous series is that you can use a formula essentially to figure out the ratio of carbon to hydrogens. So for example, here you have 2 carbons. If you put in C2, 2 times 2, because the N is 2, plus 2 is 2 times 2 is 4 plus 2 is 6. Oops, so it should say H6, C2H6. And if you look over here, when you draw the structural formula, this, by the way, is the structural formula where you can see how the atoms are actually arranged. You'll see there are 1, 2, 3, 4, 5, 6. So the structural formula represents structurally what the molecular formula tells you the ratio is between the carbons and the hydrogens. So this is the molecular formula, and this is the structural formula. Remember, the structural formula for alkenes and alkynes, they have 1 double and 1 triple bond. Okay, just one thing about properties, just an FYI. Remember that the more carbon atoms you have in a hydrocarbon chain, the higher the boiling point. Why would that be? Because there's more chance of attraction between molecules, so you would have stronger intermolecular forces. The other thing that's written on this slide that you may need to know, we talked about the molecular formula already. We talked about the structural formula. Empirical formula is just the formula in lowest terms. So if you wrote the molecular formula, if the molecular formula was C2H6, the empirical formula would be C, divide both by 2, so C1H3. Okay. All right, so how do you name an isomer? The way you name an isomer is you look for the longest chain. The longest chain, and you count the carbons. 1, 2, 3, 4, 5, 6. That parent chain has 6 carbons, all single bonds. 6 carbons, all single bonds, starts with the prefix hex, and because it's all single bonds, it ends in ANE. Then you have to notice the side chain. The side chain in this case has 1 carbon atom. 1 carbon atom with 3 hydrogens around it. If it had 4 hydrogens around it, it would be called methane. But because it only has 3 hydrogens around it, we change the ending to methyl. And then we have to give it an address. Remember, you always give it the lowest possible number address. So here, if we started counting from the chain here, it would be 1, 2, 3, 4, 5, 6. And on the second carbon, that's where we'd find the methyl group, 2-methylhexane. What would happen if I wrote it like this? 1, 2, 3, 4, 5, 6. We still have hexane, but the methyl group now is in a different place. Or is it? Look, remember these are three-dimensional structures. If I start counting from this side of the chain, the lowest number of the carbon that the methyl group is on is still carbon 2. It's just been flipped around. Remember, these structures are three-dimensional. Now, this is a little bit confusing because really what you need to know is you need to know what an isomer is in order to solve this problem. And an isomer is just something with the same molecular formula, but it has a different structural formula. So how do you figure that out? Well, these are called condensed structural formulas. And all you would do to solve this problem is you would figure out what the molecular formula is. How do I do that? I count carbons, hydrogens, and oxygens in this case, or if there were any other elements. So I'm going to show you the answer is 1, 2, 3 carbons, 1, 2, 3 carbons, 3, 5, 6 hydrogens, and 1 oxygen. 3, 6 hydrogens, and 1 oxygen. They have the same molecular formula, different structural formulas. Okay, now organic functional groups. So this is table R, and these are functional groups. They're kind of like, sometimes like side chains. They give the compound, or they help identify, if you have different functional groups, you are going to have different chemical and physical properties. Now, this chart is very important to you. If you look at this example, it will tell you how to name any compound that includes one of these functional groups. This R right here, if you read down here, it just represents a carbon chain. So let's give you an example of an aldehyde. So an aldehyde, if we write, remember aldehydes are tricky because if you're going to write a condensed structural formula, you use the abbreviation CHO so as not to get it confused with an alcohol. So the minute you see CHO, you know it's an aldehyde. So we come over to the table and we look and we see, okay, it has an AL ending. So I know because this is an aldehyde, it's going to have an AL ending. And it has how many carbons? 3. I know the prefix for carbon is prop. And then I look over here and I say, okay, it's propane, but we change the ending to al. Okay? Next, I'm going to take you through the organic reactions in a separate video. I'll post that one on Monday. Okay, the last little unit, or the last unit that we covered, is nuclear chemistry. Okay, if you want to complete this table, you can turn to table O. Okay, the mass of alpha, well, alpha you should recognize looks like this, is a helium nucleus. Beta is the same as an electron. Positron has a positive, it's a positive electron, and gamma is just energy. So gamma has no mass and no charge, whereas alpha has a mass of 4, the top number is mass, and it has a charge of +2. Beta has no mass and a charge of -1, and positron has no mass and a charge of +1. Oh, the symbol, I put them over here, but you can add them in over here. The other thing you should be aware of is penetrating power. Remember, the alpha particle is the least penetrating. It is very large and unwieldy, whereas the gamma is the most, and the others are somewhere in between. All right, now this is natural transmutation. It's natural, meaning it's going to undergo spontaneous decay. It's spontaneously going to decay into a new nucleide. So it's transmutating into a new nucleide plus some sort of radiation. This is the radiation up here, a type of particle that is released from the nucleus. So how do we figure that out? We have to balance the masses. 14 on top here, we have 14 here. So this X is going to have a mass of 0 because 14 plus 0 gives you 14. And here the carbon has an atomic number of 6 and nitrogen 7. Well, 7 plus what is going to give me 6? 7 minus 1 gives me 6. I look up on my chart and I realize that that's a beta particle. Let's do the last one just because it's a little bit confusing. You have 238 on this side and you have an alpha particle that's released. So what plus 4 is going to give you 238 and 234? And what 92, what plus 2 is going to give you 92? You get 90. And you should realize, you look up on the periodic table what has the atomic number 90, and you should see that it is, in fact, thorium. Okay, so very, very important. Most of the answers to nuclear chemistry are either on table O or they are on table N. Notice on table N, they have a list of nuclides. They have half-life and decay mode. Decay mode is whether it yields or it releases an alpha or beta particle when it is, or radiation when it undergoes decay. Okay, now the other type of transmutation you need to be familiar with is called artificial transmutation. With artificial transmutation, you have to, or people bombard a target nucleus with something else that's sped up to high speeds in a particle accelerator. So in this case, the neutron is bombarding the nucleus, and this is a special type of artificial transmutation. This is actually fission because you have the neutron bombarding a nucleus and it's splitting the nucleus into two products, two medium-sized nuclei, and it gives off neutrons in the process. This is called fission. Fission, like fissure, means to split or to break in half. That's different. Oh, and there are two target nuclei that would represent, that are fissionable. One is uranium-235 and the other is plutonium-239. If you see those two nuclei, one of them, like here, uranium-235, ding, 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 you should say, maybe this is fission. Let me check it out. Well, here's a neutron bombarding the uranium-235 nucleus, and I'm getting two smaller nuclei plus some neutrons. Yes, that would be fission. Okay, here this is fusion. We have two small nuclei, deuterium and tritium, and they need to undergo a lot of temperature and pressure, and they form together, they fuse together to form helium. They also may release a neutron and a tremendous amount of energy. Usually hydrogens are going to form together to produce helium. This is a fusion reaction. You're fusing two things together. In both cases, they're very exothermic, and they release a tremendous amount of energy because a tiny bit of their mass is converted into energy. That mass is sped up to the speed of light, and it's converted into energy by E equals mc squared. Okay, you need to be familiar with certain radioisotopes and their jobs. So like carbon-14, people use for dating previously living materials and fossils. Iodine-131 is detection and treatment of thyroid issues. Cobalt, this should say cobalt, there's a typo there. Cobalt-60 is used in the radiation treatments for cancer. This is the gamma knife. Okay, the gamma radiation is used to essentially kill fast-growing cells. And then you should also be familiar that uranium-235 and plutonium-239 are used in atomic bombs and power plants because they're fissionable. One of the big problems that you saw in your test today, actually, is that a problem with nuclear power is radioactive waste. Even though it's pretty clean fuel because it doesn't give off a lot of greenhouse gases when you use nuclear fission in order to run a power plant as the fuel, there still is radioactive waste. That's the problem. Okay, the last topic right here is half-lives. So look what it says. According to the graph below, what percentage of the radioisotope will remain after 3 half-lives? Okay, so after the first half-life, so we have 100% after the first half-life, it's 50%. That's 1 half-life. The second half-life, we're down to 25%. Third half-life, we're down to 12.5%. Let's check and see if that's right. Remember, 100%, half of 100 is 50, half of 50 is 25, half of 25 is 12.5%. That should be your answer. Okay, how many hours are required for potassium-42 to undergo 3 half-life periods? Well, you need to check out your reference tables here, and you need to go to table N, and you need to figure out that potassium-42 has a half-life of, I'm just looking it up myself, very weird, I have a reference table that is missing table N. Let me find another one. Okay, so table N, so potassium-42 has a half-life of 12.36 hours. So in order to figure out how many hours are required for 3 half-lives, all we would do is we'd say, okay, 1 half-life is 12.36, second half-life is 12.36, third half-life is 12.36. So we'd multiply by 3. Now, the general format here is you're going to start with an original number of grams or an original mass. You're going to keep undergoing half-lives. The arrows are the half-lives until you get to an end value. So look at this one. If 80 milligrams of a radioactive element, that's what we're starting with, 80 milligrams, decays to 10 milligrams. So let's make it decay to 10. First half-life, it's going to split in half. It's going to be 40 grams. Second, 20. Third, 10. What is the element's half-life in minutes? Well, all 3 half-lives together, so if you have 3 half-lives, it took 30 minutes. So if you have 1 half-life, how many minutes is going to take? So you get 3x equals 30. And you do the math and you get x equals 10 minutes. Okay, last question. Okay, after 62 hours, so 62 hours have gone by, 1 gram remains unchanged. So we're at the end. We have 1 gram of a sample of K42. How much K42 was in the original sample? Well, we've started with, we know that K42 has a half-life of 12.36 hours. We learned that already. So this is 12.36 hours. And we know that 62 hours are going to go by. So we have 62 hours divided by 12.36 is going to give us 5 half-lives. Divided by 12.36 gives us 5 half-lives. So we know after 5 half-lives, we're going to end up with 1 gram. So I have to draw 5 arrows representing 5 half-lives. 1, 2, 3, 4, 5. And I want to know how much I started with. Well, I know that if I start with an amount and I undergo a half-life, I divide by 2. So if I'm ending with this amount, I have to double it for every half-life to figure out what I originally had. So here's 1 gram. I double it. I become 2 grams. And then 4, and then 8, and then 16, and then 32 grams. Okay, thank you very much. Study hard. I look forward to seeing you on Monday.